Alright, so now let us sort of visit our single tandem, right, tandem of queues. So tandem of queues is a special case, right. So tandem of MM1 queues, to do the evaluation you can calculate the number of customers in each of the queues, simply add them up, right. So therefore you can evaluate all of them independently, that is a so called product form network, right. So for this for example, if I have a queue, right, so lambda equals 10 and say mu equals 8, that feeds into a second queue. I briefly gave you the derivation for E of n, right, total number of customers in the system. So for this system, what is E of r? So how do you compute E of r? E of r is simply the resident the response time in Q1 plus the response time in Q2, right. Therefore this is simply 1 over, or did I get it the other way around? I shouldn't have had this as 10. How about that? Let's make this 5, right. So your lambda should be less than both mu's for the system to be stable, right. So this is simply 1 over and whatever that works out, right. So 1 by 3 plus 1 by 2, so 5 by 6. So that is the E of r, and this applies to any series if you have several others. So this is a special case, right, where you are going through multiple servers in tandem. Now everybody is awake. I should be awake. So 4 by 3, is that better? Okay. So this is one particular form of product form network, right. So then there has been other works that people have been slowly proving one class after the other, right, that such and such class of networks is also closed product form, right. So some of the classic results, right, so product form networks, so based on Burke's theorem we could show that tandem queues we can evaluate, that is a one special case, right. But what if you have a set of networks of queues, right, we saw before open and closed and so on, right. What if I have a set of MM1 queues where there is some probability of moving from one queue to the other and so on, and it is an open queue, right. So what Jackson proved, this is Jackson's theorem, showed that any open queuing network with exponential service times also is a product form. So that is one of the classic results in the 60s and 70s, and then there is one more, well, few more results. This is 1963 if you are interested, okay. And then there was another theorem which is by Gordon-Newell, and the thing is this is it can also be M server queues, right, open network with so it is not just MM1, even it is MMM, right, this applies, even Burke's applies to MMM which we did not really talk about, but Burke's also if you look at the system that is will be this output. So Gordon-Newell then proved that it is not just for open network, it is also for closed networks, but the same condition, the exponential service time is what they all initially worked upon. Okay. So here they showed that in a closed queuing network with of M server systems and exponential service time. So product form network. So this is the second result, right. If you are keen, you can go back and check out some of those older papers as to how they showed that. But in both these cases, the restriction is that the service time is exponential. Okay. So what does this enable? This enables us to essentially treat all the queues independently, compute the service times and those. That's what we will see. Next sections will be on how to analyze queuing networks and try to find out waiting time and response time, number of customers in the system, throughput, all of that. With the help of these results is what we can, right. Sometimes we intuitively just say, oh yeah, just add up the numbers of customers in each of the queues, and that's the total number of our numbers. It's probably okay, but delays, for example, right, you can intuitively make some guesses, but it's better to have some proven results that you base your results on. Okay, and then there are another class. I'm sorry, this doesn't say anything about the arrival time. Only that the service times are exponential. But we go back, look at the original paper, see if they really also required Poisson, right, in that particular case. Okay. So then there are I guess there is one class called the BCMP class, okay, which I am going to skip because this talks about other types of queues also and other types of service disciplines, right. For example, processor sharing, they call it first come first served processor sharing, and as well as not last come first served. So about 3 or 4 particular types of service disciplines besides FCFS, and some other restrictions on exponential is still there, but the type of disciplines that you can use besides FCFS, you can have other disciplines too. So that's what this BCMP has, another set of conditions. So any queuing network that satisfies this so called BCMP conditions. BCMP is named after the authors, right, and if you really want, it's basket. This will not be on the quiz, but and this was in like 75. They showed for a larger class of networks, right, that this set of product form solutions is possible. So
will it actually affect arrival time distribution?
No, but your response time will change if it's LCFS versus FCFS. So like processor sharing, if you look at it, processor sharing results are there in I think Raj Jain. There the mean time does not change because the order of scheduling does not affect essentially your mean time, but the variance and delay can be different, right. That's where it will be. So first order moments might be the same, but the other moments will be more complex.
So processor sharing can be modeled like MMM.
Process, no, this is MM1 with processor sharing as a scheduling discipline. So it is not, whereas what we talked about is FCFS, right. There is a difference. In FCFS, once you take a customer, you service the customer completely. With processor sharing, you service each customer for a very tiny duration. It's like round robin, right, and then you keep going to the next customer. It's not even round robin, it's usually larger quantum. This is like on a bit by bit, right. So it's an extremely small time is allocated to each customer. You service and then go to the next customer and so on. So with that, essentially you will end up with the same average time. Mean time will not change, but the other parameters will change. That's what they try to show in this case, and those things we will verify with simulation, right. When we give MM1Q, I will give you for FCFS. The same Yaxim code also supports LCFS, for example. What if I have LCFS as a queuing discipline? What will happen, right? Then you can see LCFS will always lead to, it can lead to starvation, right, if it's last come first served. The guy who came first might forever sit there until the queue gets empty, is going to be sitting there. But those things we can play around easily with simulation and see what are the stable operation conditions. Okay. So that will be your second project, second assignment that will come up. And then third assignment, the plan now is to have queuing networks, right. First will be simply set of queues with maybe tandem queues also we can try out, and then after that the last assignment will be with set of networks of queues, by which time I would have covered all the open networks and closed queuing networks, MVA, all that will be done. So you can actually, we will do this, the theory is there, you also have the simulation to show that whether the theory is correct or not. And the nice thing with simulation is that I can say exponential only, this formula will work, but what if it is not exponential? So you can simulate non-exponential service times and then compare those results to the baseline exponential, right. So in future you can always say exponential gives me one sort of trend setting or some sort of lower bounds on the system as such. Okay, so this is the sort of set of things that will come. So what we look at next is, so before I go to queuing networks, because there are going to be a couple of weeks in which there will be some classes missed, I want to start queuing networks afresh if possible. In worst case I'll have to start sometime next week also, or on Friday itself. Okay. So now I promised some time back, right, we will look at this slotted Aloha model as a Markov chain with a slightly different perspective. That is one that is pending, and we also, I said I also talk about semi-Markov models. So we talked about Markov, right. Semi-Markov models is just another extension, and sometimes it's useful to it's just possible, you just cannot make everything as an as a Markov chain, so you have this so-called semi-Markov models. Okay, all right. So now let us look at slotted Aloha. And the reason we do that is, yes, Aloha is a very easy protocol to simulate, right, in the simulator, discrete event simulator. So we will have some simulation numbers, okay, and we always would like to know, right, what is the theoretical limit. The theoretical limit that we saw, one is a g e power minus g, right, which is a very gross result. We saw the other model also, where you have a set of, right, states, and then you're looking at the number of users in the system. So that is one way of looking at modeling the system, right. In that system the state was captured as the number of backlogged customers, and the others are unbacklogged, and you are trying to see how the system transitions, right. So if any of you actually attempted that problem on their sample assignment, if you try to build it, and right, you could have seen. Now that you are not, it's okay. We will look at a different model, right, and then see whether this is actually implementable also easily. When as part of your one of the assignments we will include Aloha. Aloha code is there, already have written that. It might have bugs in it, so I'll expect you to fix it. That code is 20 years old, right. So this model that I'm going to talk about is something that was my first Markov model. So you are stuck with it, right. So you have to see what this Markov model is all about. But anyway, I think it's still useful, right, and we can verify whether my model is correct or not. No. So now this model for Aloha is going to be based on a single user's perspective. Okay, so there is a notion of a channel, right. So there is a common channel that is being shared. There is a channel, and then like before we have a set of users, right. So this assume that this represents the NIC card of every user, right. So the NIC card, this is your right MAC card that is implementing Aloha. So I will model that as a server. And then the MAC card is getting packets from which layer? Okay, it can be from both layers. So let's assume that the packet is coming from the IP layer, because whatever comes from the physical layer simply goes to the IP layer. So therefore there is not much of sharing is done, right. Sharing is needed only when you want to send a packet. So therefore these are packets coming from the IP layer. Okay, so packets are coming from IP layer, and let's what did I use here in those days? Okay, lambda. All right. So lambda packets per second is the arrival rate. So there is every, right. So now in the simulator you can imagine I can simply build, right, one process or one event group of events for handling a particular user, and then simply replicate that as many times. If 1000 users, I can simply replicate by 1000, right. I can essentially create copies of this. Okay. So now the modeling is based on the user's perspective, not from the system perspective. So what are the states that each user is going to spend, right. It goes through different stages. Okay. So to actually model that, we had one restriction, right. So so this is so called the 2 buffer model, which means there can be one packet, right, trying to be sent, and then one that is queued. So packets arrive to this queue at most B, in this case only 2, right. We can generalize this to B buffer model if you want to, the same model can be expanded, but let us look at a 2 buffer model because it is easy to deal with. Okay. So let us define a few parameters that we will need here. Okay, there are 5 states, right. So S naught represents the state that this is modeling the transmitter of every user. This is one particular user that I am modeling, right. So this is modeling that the user's transmitter is idle. Basically there are no packets to be sent in the queue, right. This is one particular user's queue that I am looking at, no packets in the queue, therefore the transmitter is idle. Okay. And the transmitter, if in Aloha, will be in 2 possible states essentially, right. So one is when a packet arrives newly to the queue, always try to send, right, therefore you are in transmitting stage, and at the end of this is a slotted Aloha, right. So therefore this is DTMC, every one slot is one packet will solve, right. So if I have a packet at the beginning of a slot, I will send the packet. At the end of the slot, either there is a collision or there is success, right. If there is a collision, then I go into back off stage, right, that is the definition of Aloha. And in back off, what do? We saw last time, right, there is a back off probability PB, right, what we had A and B last time, right. So if you are in back off, there are different ways you can come out of back off, right. One is to simply schedule, treat that as a uniform interval, uniform between 0 and 20, right. Anytime between the next 1 and 20 slots, the transmitter will wake up and try to retransmit the packet. That is one model of the back off, handling back off. The other is you simply have this probability PB, where in every slot you will keep flipping the coin like geometric process, right, keep flipping and then decide to send or not, or Bernoulli/geometric. So that we will assume the second one, where in every slot there is a probability PB of trying to resend. With 1 minus PB you won't resend, you will simply stay put, right. Okay. So S1, a transmitter is sending a packet, and there is no buffered packet. So there is the occupancy of this queue is simply 1, and then the parallel state is, it is possible that, right, I tried, I failed, and then between another packet came and it got queued, and only 2 packets can be in the queue, right, third packet comes, simply gets dropped. So, and here this is a situation where I have a packet queued and I am also trying to transmit the packet. So there is no buffered, I mean no additional packet is buffered, right. So there is one packet in the buffer, which is the one that I am trying to send. Okay. So either transmit in every slot, the transmitter can be in one of these states, either sending or simply sitting in back off even though there is a packet to be sent, or in idle because there is no packet to be sent, right. So this is S3 is a transmitter in back off state, with no additional packet buffer. And S4 is ditto as S3, except there is one packet buffer. Yeah, total queue length is 2. Yeah.
We are assuming queue length to be 2.
Yes. The total buffer capacity in the MAC layer card is only 2. It can store 2 packets. Yeah. So one under transmission, second one is simply waiting for service for the first one to be sent, and it is simply first come first served, right. So until the packet at the head of the queue finishes successfully, the second packet cannot be sent. Make sense? Okay. One additional packet, yeah.
But you already in a back off state, right?
So there are a total of 2 slots.
Okay.
So I am in back off. So let us say only one packet has come. One packet is sitting in the queue, and I am trying to send it. It failed, and no other packet has come for a long time. Therefore, that is when S3 is. but in the time that I am waiting, because I am back off, I try to send right, in every slot is some probability PB, so some slots I will never try to send at all. In that time if one more packet comes, right, then the occupancy of the queue will be 2.
So you are assuming that there was no packet before I got into the back off state in S4 state.
In S4, okay, see S4 state will happen, and this is the sequence. You are in S0, right? Okay, I will draw that picture, right? Then let's look at the transition diagram, right? The state machine. Then you will be able to figure this out. Okay. So any questions on, right? These are the states. I am sending, no other packet is waiting. I am sending, but one packet is waiting, and I am not sending in back off. Either there is a packet or there is no packet. S4 buffer is full. Yeah. Even S2 also buffer is full. Yeah. S2 and S4 all slots are used. S1, S3 one slot is free for some packet to come. And we assume that, okay, we will make some assumptions, right. Okay. So we will have to make some definitions. So beta is the probability that at least one packet is generated. This is at a given user, right, in one slot. So if the queue is empty, okay, and we will have to make a small assumption, we can relax that if we really want to, which we will give slightly more improved performance, right. We will assume that in one slot only one packet can be generated, no more than one. If you really want, we can change this model to simply do that also. It won't, we can do that, maybe we will make that as your exercise, right, change that and see whether it makes that big of an improvement to your performance model. But sometimes these things will make a difference, sometimes it might not. If I do not assume, depends on the lambda value that I am looking at as well as your time slot, right. If time slot is very large, then saying that only one packet will come in a time slot is a little bit of an approximation. It is possible that more than one will come, but we will just assume that at most one packet is going to come. This is all per user. This entire model is on a user's perspective.
In one slot.
In one slot, yeah. This is per user, right. So what is this going to be? Given that the arrivals are right, so we have Poisson, right. I did not say that, but I am saying this now. Poisson arrival rate, that lambda, right, which I mentioned earlier. This is per user. It is not the system wide. So what is this going to be? Probability of no packet getting generated in Poisson is e power minus lambda, right, because lambda and t equals 1 here. So this is simply 1 minus, and I will call beta to be 1 minus beta bar, right, to be simply 1 minus beta. I could have simply called e power minus lambda, but anyway I have to follow my okay. So what other parameters do we need to know? So beta is the probability of one packet, at least one packet coming. I need to know the probability of success, right, probability of when I send a packet, what is the probability of success? It can be 1 if there is no other user in the system, but it will be not be 1, it will be some smaller number if there are several users in the system. That we will have to figure out, right, if there are n users trying to compete, and what is the probability, right, that I will succeed. That will be actually a binomial, right, we will come to that later. So PS is the probability of successful transmission. That will depend upon how many users are there in the system, but simply assume that there is some variable called PS, right, that we can compute, that will be a single value, which is we are only looking at steady state analysis, and PB is the probability of the back off probability, or probability of transmitting while in a back off state. So if I am in back off, I will flip a coin with probability PB, I will try to resend, and with 1 minus PB I will stay in the same state. PB can be 1 if you want, right, that becomes very aggressive. If PB equals 1, what will happen? 4 users collide, everybody then keeps on trying in the next slot, nothing is going to go through. So PB has to be relatively small, but PB is very small, then your 1 over PB is that number of slots you have to wait before actually you will try to send, right. The expected number of slots before actually retransmitting will be very large if PB is small, because I am only say probability PB is say 0.001, right. It will take me 1000 slots before I even try retransmitting, and that is extremely passive, the other one is extremely aggressive. So this is a design issue, right, what value of PB is going to be. So that we will have to assume is given to us. In a real system PB is actually not static, it is dynamic, right. You look at the system, how many collisions you have, and then try to adjust your blackout probability based on that. In this analysis I can only assume fixed PB, right. If I go to dynamic PB, my model will simply collapse, so therefore I have to deal with it. But in my simulation I can do whatever I want to, and then see whether varying the blackout probability makes a big difference or not, right, dynamically, that is, okay. So this is our setup so far. Now we come to the picture. Okay, so we are in state S0, so S0 is the idle state. So the system will start in state S0, right, that is the initial state, and then with there are two events that can happen when I am in idle. This is a slotted Aloha system, so all event changes take place only in the beginning of a slot, right. So we do not change state in between, that is the again convenient assumption that we are making. So if I am idle in the beginning of the slot, in the next slot beginning I would be either having a packet to send if some packet had come in this one slot, or I will have no packet to send, right. So this is beta bar, this is beta. So this is assumption I am making, right. I could have made this as no packet is e power minus lambda, one packet is e power lambda, lambda e power minus lambda, more than one packet is 1 minus these two things, and then sent this to S2 also. I could have gone from S0 to S2 to give a little bit more accuracy, but I am just making that simplification. Okay, so either only one packet will get generated and simply get sent to the queue. Okay. So now how will we, let us say draw these other pictures also. I will draw S2 here. So from S1 I have a packet to send, so beginning of a slot there is a packet to be sent. What will be the next possible states? What are the transitions and what are the state transition probabilities? S1 to, I can go from S1 if a packet is successful and no packet is generated, I go back to S0. Okay, so let us deal with that first. So what is the probability for that occurring? Or beta bar, right, packet successful and no packet generated, so I go PS into beta bar. I can have a self loop also, right, if I successfully send this packet and a new packet is generated, I will stay in the same state. Then what else can happen? Can I go from S1 to S2? I cannot go from S1 to S2 because S1 to S2, which means S2 there is a packet queued, but assuming only one packet can come, right, I really cannot do that. Okay, but from S1 I can go to S3. So to go from S1 to S3, it means that the packet was not successful, 1 minus, and no new packet was generated, so therefore beta bar. And I have one more state, right. It is possible that I tried to send, it failed, and between another packet also came. So that is a set of transitions. Then some of S2 is kind of stuck. Okay, let us look at S3 next. So I was unsuccessful in the previous slot and no packet came, right. From S3 then what are the transitions? I will go from S3 to S3, which means I did not write back retransmission and no new packet came, right. So this is 1 minus PB into backoff probability. PB is my retransmission probability, I would call that probability of retransmission. And tried and failed. No, I only move from backoff to transmit state. Okay, this whole right, and the entire state I was in backoff. Next state I am going into the transmit state. So that will be here. So this is PB, and no packet was generated because I am now in transmit mode at the beginning of the slot, but there was no packet in the previous slot. Okay. Then we can go from S3 to S2, can't we?
Go to S0 with PB into beta 1 because I successfully transmitted a backlogged packet.
No, you have not successful. You are only moving to transmit state. At the beginning of the next slot, you are in transmit state. You didn't send yet. Okay. So I was in backoff at beginning of the slot. At the end of the slot, did I choose to go to transmit or not? And the next slot only I will send. Right. So this entire slot was spent. And here again I might have sent, right. I am trying to send in the next slot, and there was a packet generated. So have we satisfied all the transition of S3? Not yet. So S3 I can stay, I can go to S4 if I did not, if I have decided not to retransmit in the next slot and one packet came. So alright, so then in S4 I can, what are the transitions possible in S4? S4, whatever new packets arriving makes no difference, everything is going to be dropped, right. So either I try to send or I do not try, either try retransmission or rotate retransmission. So therefore this is simply going to be 1 minus PB, only two transitions. S2 I am ready to, I am trying to attempting in this particular slot, either I am successful or not successful. New packets don't make a difference because the queue is already full. So this is going to be, if I do not succeed, 1 minus PS, and if I succeed, PS. If I succeed, I go back to transmission with one packet, right. There is still one packet to be sent. I had two packets. As there is no room to store. See, I am only two buffers are there, right. So I am at the top of the buffer packet. I am trying. In between, in that one slot, if anything happens, if a new packet comes, it is simply going to get dropped. Therefore, there is no room for it. I think that essentially, right. Now what do we do? So we can now try to, we want to find out throughput, delay and things like that, right, okay, for a particular user, right? But before that we need to know the steady state probabilities of each state, right. Okay. So let us, so what we can do is we can solve Vp equals V sigma Vi equals 1 to get the there is only one catch though. PB is specified as an input, lambda is given as the input. These are only two things we needed, but this PS is actually a system dependent. Okay, so PS will actually depend upon the probability of success. PS actually will depend upon the number of users trying to compete in the system. So how do we model that? So we somehow what is happening is now I am having an iterative process, right. I can compute the PEs, but unfortunately do not know PS, and the PS depends upon the P's actually. Okay, so what is the probability that a node will attempt to send a packet. In a slot. We will call this as sigma, right. For a node to be in transmit state, what is the probability? That it is either in P1 or P2, right. So if I know P1 and P2, I can simply say that I am in transmit state with probability sigma, one of those two states I am sending the packet, okay. Now there are n users sending the packet, right. If the total of, let us say, n users are there in the system, so each of them, assume that the system is completely IID, right, every node is behaving identically, so in the long run they will all have the same piece. So if I have n users, each of them with probability sigma of being in a transmit state at in every slot, then what is the probability of success? Simply n choose 1, right, or with well it is yeah, tell me that there is only one state or one process or one user in this transmit state, others are all in the non-transmit state, right. So that is our binomial basically, right. So therefore I can approximate this is where we always have confusion whether the extra sigma is needed or not. Given that I am in the transmit state, I want everybody else to be quiet, only then I will succeed, and given that there are m users in the system, I will succeed if nobody else sends. If you are going to fight with me on whether sigma is should be there or not, right. Yeah. Yeah, so this sigma battle I have fought in fact I have a more complicated expression, but this is the simplest one, 1 minus sigma into m minus 1 actually will should take care, but adding that sigma did not work, I have tried it. So if you want to cannot, because this is assuming that I will get your question, that this one user in transmit state, right, what is the probability that I will be successful is if nobody else sends, therefore only other m minus 1 users should be not in the transmit state, right, any other state that they are there, yes. Okay, see this is our these are the two transmit states, right. If a user is in S1 or S2, it means the user is sending, and the probability of that where P, right, our P of n, P of 2 is the steady state probability of being in state 1 and state 2, okay. Let us kind of add that, right. Oh yeah, we said V1 and V2 and I said P1 and P2, okay, that is what happens, I refer to my book. So this technically is V1 and V2. Probability of being in state 1 or state 2, right. So now I have PS equals this, right. So now I have a set of Markov equations which I can simply plug into, right. In fact, if you those days I used to actually manually solve, right, I will write out this whole expressions like you do in your test and then solve it. We had MATLAB or Mathematica at that time, which which I didn't really use. I will simply solve this equation, then plug those equations into only the equation solver to say V naught equals and so on. But anyway, so I can come up with the transition matrix, then I have to initially start with some value for PS, right. So the way to solve is right, assume PS equals some small value 0.001 or something like that. I forget what I used to do in my olden days, and then solve. So because I am assuming taking some, right, then solve for the vector V and PS and then repeat until convergence. You have to have some condition for convergence saying that ultimately my sigma converges to some small, right, sigma 1 in the first iteration. If I get sigma equals this, the second iteration if you get different sigma, then the difference should be some small epsilon, right. So repeat until convergence on some parameter, whether it is PS or sigma, whatever it is that you want. Once you find that there is no change in the transition probabilities and the way that you the steady state probabilities, then you can stop, right, repeat right. So you need PS to start to compute sigma, then you use the sigma to recompute the PS and then do this forever. And what we found is about 50 iterations in most of the cases, things would converge. But if lambda is very large, of course it will not converge. Well, lambda is actually probably it will still, whatever it is, lambda is large, is going to go toward minus about, sorry, it will go towards 0.36 or something like that, right? Okay. Okay, so then now I have the steady state probability of being in each of these. Now what is the throughput of the system? What is the throughput of the system from the user's perspective?
Total number of packets successfully transmitted over time slot.
So per user's probability of success is sigma, right? So it will be simply sigma or sigma into m.
Sigma into n.
So each user's throughput will be a share, right? It is only per user throughput that I am seeing. So it will be the user total system throughput will be sigma into m, because sigma is the probability of, no sorry, PS into m. PS is the probability of successful transmit, not sigma, right? PS is the probability that I will successfully transmit, and it's got to be m into PS. Yeah. Okay, some approximations are there, we will see. If not, think before next class, because I want to stop in a couple of minutes. And then delay, how do you find delay?
Is it PS into M?
Why is it PS into m? Okay. So the probability of a node successfully transmitting in a slot is PS, that is my throughput. Per node throughput is PS, right? PS is also the per node throughput, PS.
PS into n.
Probability of successful transmissions, yeah, given that I am in sigma into PS into m.
If I have a packet to send, then I should succeed.
Yeah, okay. So that's where that again that one sigma is there, right? Sigma into PS, probability of being in a transmission state, and probability, so sigma into PS. Okay, that into m will come because I am looking at the system throughput as such, because each user throughput will be less than that. Okay, that we will come back and continue. And delay per user is easy to find out. How? I can compute E of n, right? Remember the reward function business? I simply say the number of customers here is 0, number of packets here is 0, this is 1, this is 1, 2 and 2. Look at the probabilities, right? I can compute the average buffer occupancy of the queue in the system by using the reward function. Once you know the steady state probabilities, I can compute the average number of packets in this queue. That divided by lambda is my delay. So this is how I can compute delay and throughput in the system. Okay. I will continue on specifics of that with the next class, but that is the basic principle, right. So now if I give you a system with m users and lambda and PV, simply crunch out these PS, B and so on, write an equation, iterative equation that will simply solve this. Right. You can write it in C and then interface to something else, or actually you can even solve the closed form equations very simply if you want to. You will simply have a set of closed form expressions that you will solve with, that will give you all the values for all of these. Okay.
In this system, the user will wait at least one slot before retransmitting.
In this particular system, at the end of no, I
then I have to wait one slot before retransmitting.
That's correct. Yeah.
But in real system, you can retransmit in the immediate next.
Yeah,
slot.
you can. Yeah. So then, if I really want to include that, then my S1 from S3 to S0 I could go. Yeah. If I don't want to wait that one slot. Yeah. So yeah. So these are some of the approximations that you try to do. Or in which case, yeah, S3 will also be a transmit state then, right? So S3 will, if I allow S3 transmission in S3, then I will have to change my parameters, my transition properties accordingly, but S3 will then also be a transmit state. Then sigma will be equal to whatever P1 plus S2, right? V1 plus V2 plus V3 plus V4. If all of them I can have transmission, so that one extra slot will make a difference. Okay. So this is using plain Markov, right? Now what you find is that, in just 2 minutes I will say and then stop. See, the self loops are here, right. This is a right, so I can replace all these self loops, right, by simply stating that rather than have this system move on a slot by slot basis, I can have the time spent in each state to be anything, in this case it will be exponential, right. I can simply replace this self loop and replace this beta by 1. I will come back on this. Your quiz 1 problem will we can do this approximation with Semi-Markov. I will come back and deal with Semi-Markov separately. I can replace self loops basically with the sojourn times of each state. I do not need to have, right, I do not have to have this extra self loops. I can remove the self loops and then instead I will say S0, the time spent in S0 is basically 1 over beta, right, and then with that I can, all these self loops can be replaced with just corresponding sojourn time in each of the states. Then I can again recompute this, then it becomes a Semi-Markov model which we will come back and deal with on Friday.